Deep in the vast silence of space, hidden among the stars, something strange is happening, something that defies everything we thought we knew about the universe. Imagine a signal so powerful, it crosses billions of light years in the blink of an eye, carrying more energy than the sun emits in decades, all packed into a burst lasting just milliseconds. These aren't the whispers of distant galaxies. These are fast radio bursts, FRB, some of the most baffling, electrifying cosmic mysteries ever detected. And here's the thing, we still have no idea what's causing them. Picture this, you're an astronomer scanning the skies one ordinary night when suddenly a blip. A flicker of radio waves so intense, so fleeting, it's gone before you can even process it. That's exactly how the first FRB was discovered back in 2007. Since then, these enigmatic signals have been popping up across the cosmos, each one a tantalizing clue wrapped in a riddle. Some repeat like clockwork. Others vanish without a trace. Some seem to come from the edges of the universe, while others might be lurking right in our cosmic backyard. And with every new detection, the mystery only deepens. That's why we're diving deep into the heart of this cosmic puzzle, unraveling 30 of the most mind-bending mysteries surrounding FRBs. From bizarre theories about alien megastructures to the violent deaths of neutron stars, from the whispers of hidden dimensions to the possibility that these bursts are rewriting the laws of physics. This is a journey to the frontier of human knowledge. So buckle up, because by the time we're done, you'll see the night sky not as a static canvas, but as a dynamic, chaotic, and utterly mysterious place where even the briefest flicker of light could change everything we thought we knew. The universe is speaking, and we're just beginning to listen. The story begins quietly, buried in old data from the Parkes Radio Telescope in Australia. It was 2007, and astronomer Duncan Lorimer was sifting through years of observations when he stumbled across something that shouldn't have been there, a single, blistering burst of radio waves lasting just 5 milliseconds, but packing the energy of 500 million suns. At first, it seemed impossible. His team checked for instrument errors, interference, even potential glitches from passing satellites, but the signal was real. And it had come from so far away, its journey spanned billions of light years. They'd just discovered the first fast radio burst, later nicknamed the Lorimer Burst, though at the time no one even knew what to call it. What made this detection so extraordinary wasn't just its power or distance. It was the fact that for years, astronomers had overlooked similar blips in their data, dismissing them as terrestrial noise or equipment quirks. But Lorimer's burst was different. It had a telltale signature, a dispersion effect where lower frequencies arrived slightly later than higher ones, stretched out by the thin gas of intergalactic space. That delay was the smoking gun. This wasn't some local disruption. This was a cosmic scream from the other side of the universe. The discovery sent shockwaves through astronomy. Here was a phenomenon so fleeting, so enigmatic, it challenged the very way we study the cosmos. Traditional telescopes are built to observe slow, steady object stars that burn for millennia, galaxies that evolve over eons. But FRB, they're cosmic fireflies, flashing once and vanishing before you can blink. Suddenly, astronomers realized the universe might be filled with these invisible, high-energy fireworks flickering in the dark. And if that were true, it meant we'd been missing an entire layer of reality hidden in plain sight. Lorimer's burst opened the floodgates. Within years, more FRBs were uncovered, some repeating, others one-offs, each one stranger than the last. But the mystery only deepened. What could possibly generate such staggering energy in mere milliseconds, colliding black holes, exploding neutron stars? Or something even more exotic lurking in the uncharted corners of physics? The Lorimer Burst didn't just give us a new puzzle, it rewrote the rules of the game, proving the cosmos still holds surprises that defy our wildest imagination. Just when astronomers thought they were starting to understand fast radio bursts, the universe threw them another curveball. In 2012, something unprecedented happened, a signal that didn't just flash once and disappear. It came back and kept coming back. This wasn't a cosmic one-hit wonder. This was FRB 121102, the first repeating fast radio burst ever detected, and its discovery turned everything we thought we knew about these mysterious signals upside down. The story begins at Puerto Rico's Arecibo Observatory, where researchers were combing through data when they noticed a series of bursts, all originating from the same patch of sky, all with the same peculiar fingerprint. At first, the team thought it might be a glitch, but as the bursts kept reappearing, sometimes days or weeks apart, the truth became undeniable. Whatever was producing these signals wasn't destroying itself in the process. That single fact sent shockwaves through the astrophysics community. Until then, the leading theory suggested FRBs were the death cries of massive cosmic objects colliding neutron stars, evaporating black holes, or other cataclysmic events that could only happen once. But FRB 121102 shattered that assumption. Whatever was behind these bursts wasn't just surviving, it was thriving, firing off multiple signals like a cosmic lighthouse with no apparent rhythm. Even more astonishing was the burst's location. When astronomers finally pinpointed its origin, they traced it to a dwarf galaxy 3 billion light-years away, a small, unassuming neighborhood of stars not unlike the early universe. But nestled within that galaxy was something extraordinary. A highly magnetized neutron star, or magnetar, spinning furiously and enveloped in a nebula of turbulent plasma. Suddenly, the repeating bursts began to make sense. This wasn't just any cosmic object, it was a powerhouse capable of generating immense energy over and over again. Yet the mystery only deepened. What made this particular magnetar so special? Why did its bursts sometimes cluster together, then fall silent for months? And if neutron stars could produce FRBs, why weren't we seeing more repeaters? The discovery of FRB 121102 didn't just rewrite the rulebook, it tore it to shreds. It forced scientists to reconsider every assumption about what FRBs could be, opening the door to wild new possibilities. Maybe some bursts came from magnetars caught in the throes of stellar tantrums, while others were the work of entirely unknown cosmic engines. Maybe repeating and non-repeating FRBs were two sides of the same coin, or completely different phenomena masquerading under the same name. One thing was certain: the universe had just shown us that when it comes to fast radio bursts, expect the unexpected. And as if to drive that point home, FRB 121102 had one more surprise in store. In 2020, astronomers noticed something bizarre. The bursts weren't just repeating, they were following a pattern. Every 157 days, like clockwork, the source would activate for roughly 90 days, spewing intense radio waves before abruptly going silent. Then, after 67 days of quiet, the cycle would begin again. This wasn't random chaos, this was precision, a celestial metronome ticking across billions of years. What could possibly create such an intricate dance? Some theorized the bursts might be tied to the orbit of a companion object, perhaps a neutron star locked in a gravitational tango with another dense cosmic body, its bursts flaring up at predictable intervals. Others wondered if the magnetar itself was wobbling like a spinning top, its magnetic fields twisting and snapping at regular intervals. But no single explanation could account for every quirk of this celestial enigma. FRB 121102 proved one thing beyond doubt: the universe is far stranger than we ever imagined. It showed us that fast radio bursts aren't just cosmic accidents, they're messages, written in a language we're only beginning to decipher. And with every repeated burst, they whisper the same tantalizing question: what else is out there waiting to be discovered? The cosmic puzzle of fast radio bursts took its most shocking turn yet in April 2020, when astronomers witnessed something unprecedented, an FRB exploding from our own galactic neighborhood. For the first time, one of these mysterious signals didn't come from billions of light years away. It came from inside the Milky Way, erupting from a known object just 30,000 light years from Earth. This wasn't just another detection. This was FRB 200428, and it would become the Rosetta Stone that finally linked these enigmatic bursts to one of the universe's most extreme objects, a magnetar called SGR 1935+2154. Magnetars are neutron stars on steroids, the collapsed cores of dead stars, packing the mass of our sun into a sphere smaller than Manhattan, spinning faster than a kitchen blender, and wrapped in magnetic fields so intense they could strip the information off a credit card from halfway across the solar system. Astronomers had long suspected these cosmic powerhouses might be behind some FRBs, but without direct evidence, the theory remained speculative. That all changed when SGR 1935+2154 threw a tantrum. On April 28th, space-based gamma-ray detectors lit up as the magnetar unleashed a storm of high-energy radiation. But what happened next was the real surprise. As telescopes scrambled to observe the event, Canada's CHIME radio array caught something extraordinary. A millisecond blast of radio waves so intense, it matched the energy profile of distant FRBs. Here, at last, was proof that magnetars could produce these elusive signals. And not just any signal, this one arrived with a bonus. Alongside the radio burst came an X-ray counterpart, a dual energy scream that gave scientists their first comprehensive look at an FRB's full spectrum. What made this discovery earth-shaking wasn't just the proximity. It was the detail. For the first time, researchers could study an FRB's source with precision, watching as the magnetar's crust quaked under unimaginable magnetic pressures, triggering a starquake that rippled across its surface. The energy released twisted the star's magnetic fields like rubber bands until they snapped, unleashing twin beams of radiation, one in X-rays, one in radio waves, that shot across the galaxy. Suddenly, the pieces fit. Distant FRBs might be magnified versions of this same phenomenon, their signals amplified by intergalactic distances and the extreme environments of younger, more active magnetars in the early universe. But just when the mystery seemed solved, SGR 1935+2154 posed new questions. Why had this magnetar produced only one detectable FRB despite multiple outbursts? Why did its radio emission differ slightly from cosmological FRBs? And most puzzling of all, if magnetars were behind these bursts, why weren't we seeing more from the dozens of known magnetars in our galaxy? The detection proved some FRBs definitely come from these extreme objects, but it also hinted that the universe might have multiple ways to generate them. This galactic FRB did more than solve a mystery. It revealed how much we still don't understand. It showed us that magnetars, for all their ferocity, might only be one piece of a larger cosmic puzzle. And it taught astronomers a crucial lesson. Sometimes the breakthroughs that reshape science don't come from the distant universe, but from the strange objects lurking right in our own celestial backyard. One of the most jaw-dropping revelations about fast radio bursts isn't just what they are, it's where they're coming from. The vast majority of these signals aren't just distant. They're cosmic marathon runners traveling from galaxies so far away, their light has been journeying since the universe was half its current age. How do we know? The answer lies in a subtle fingerprint called dispersion, the same clue that helped identify the very first FRB. When a radio wave races through space, it doesn't travel alone. It brushes against the sparse electrons floating between galaxies, and that interaction slows it down, but not evenly. Lower frequencies drag more, arriving slightly later than higher ones. The wider that delay, the more material the signal has traversed, revealing the mind-boggling distances these bursts have crossed. For most FRBs, that dispersion measurement paints the same staggering picture. These signals originate billions of light-years away, often from galaxies so young, stars were still forming at a ferocious pace. Here's where the physics gets dizzying. To produce a radio burst bright enough to remain detectable after such an epic journey, the source must unleash staggering energy, equivalent to 500 million suns shining together for those few milliseconds. That's more power than some supernovas release in months. But unlike a supernova, which unfolds gradually, an FRB packs all that energy into a cosmic snap of the fingers. Whatever's creating these bursts isn't just powerful, it's efficient, channeling unimaginable forces into a fleeting instant. This extreme energy requirement throws a wrench into nearly every proposed explanation. Take neutron star collisions, violent mergers that were once leading candidates. Even these cataclysmic events struggle to account for the raw power needed, especially since some FRBs repeat. Magnetars, those cosmic powerhouses in our own galaxy, come closer, but they'd need to be in a perpetual state of hyperactive tantrums to match the brightest bursts detected from across the universe. Then there's the question of survivability. If some FRBs truly come from the universe's toddler years, their sources must have existed in environments far more chaotic than anything we see today. Picture a young galaxy thick with newborn stars, exploding supernovas, and swirling magnetic fields. A pressure cooker where even magnetars might not last long enough to produce multiple bursts. Yet somehow, against all odds, these objects not only survived but thrived, screaming their existence across cosmic epochs. The distance problem forces us to confront an unsettling possibility. We might be missing a fundamental piece of physics. Could there be exotic objects we've never detected, cosmic engines far stranger than anything in our current playbook? Some theorists speculate about blitzars, hypothetical supermassive neutron stars that collapse into black holes in a spectacular final burst. Others wonder if FRBs are the death cries of cosmic strings, topological defects left over from the Big Bang itself. Or perhaps they're evidence of physics beyond Einstein's signatures of higher dimensions or quantum gravity effects playing out on galactic scales. But the most humbling realization, every FRB we detect is likely the tip of the iceberg. For every one bright enough to pierce the cosmic static, thousands probably fade into oblivion, their whispers lost in the vastness. That means the universe could be crackling with these bursts, a hidden symphony of radio waves we're only now learning to hear. And with each new detection, we're reminded the cosmos still holds cards it hasn't shown us. The deeper we listen, the more we realize how much we've yet to understand. Among all the bizarre behaviors exhibited by fast radio bursts, none has been more meticulously precise or more perplexing than the rhythmic dance of FRB 180916. Nestled in a spiral galaxy 500 million light-years away, this isn't just another repeater. It's a cosmic metronome flickering to life like clockwork every 16 days, 4 days of frenzied activity, then 12 days of silence over and over again. This isn't random chaos, it's a celestial heartbeat so regular you could set your watch by it, and it's forced astronomers to confront a haunting question. What kind of cosmic engine could possibly keep time with such eerie precision? The story of this winking FRB begins in 2018 when Canada's CHIME telescope caught its first bursts. At first, the signals seemed ordinary, another repeater adding to the growing catalogue. But as months passed, a pattern emerged. By 2020, researchers had mapped its cycle with stunning clarity. For roughly 100 hours, the source would spit out multiple bursts per hour, some separated by mere minutes. Then, as if a switch flipped, it would vanish without a trace for the next 288 hours. This wasn't just repetition. It was orchestration, a level of predictability never before seen in the FRB universe. The implications sent theorists scrambling. Cosmic objects don't just follow human-like schedules unless something fundamental is forcing them to. One leading explanation points to an orbital dance. Picture a magnetar, one of those ultramagnetic neutron stars, locked in a gravitational embrace with a massive companion, perhaps a blue supergiant star or even a black hole. Every 16 days, as the magnetar swings closest to its partner, tidal forces or surges of stellar wind could trigger bursts like a cosmic clock chiming on approach. The 12-day quiet period, that's the magnetar retreating to the far side of its orbit, its bursts now pointed away from Earth. It's a compelling idea, but there's a catch. No known binary system with a magnetar behaves this way. The timing is too perfect, the bursts too consistent. Another theory suggests the periodicity might come from within the magnetar itself. These stellar corpses can wobble like spinning tops due to their mind-bending physics, a phenomenon called precession. As the star's rotation axis slowly tilts, its beams of radiation might sweep across Earth's line of sight at precise intervals, creating the illusion of an on-off switch. But even this elegant solution raises questions. Magnetar precession is typically messier, less regimented, and why 16 days? Why not 14 or 20? The number feels arbitrary, lacking any obvious link to known astrophysical processes. Then there's the wild card. Could this be evidence of something entirely new? Some speculative models propose cosmic strings, hypothetical, ultra-dense filaments left over from the Big Bang vibrating at set frequencies, or even exotic states of matter warping spacetime itself into a repeating rhythm. These ideas push the boundaries of known physics, but FRB 180916 seems to relish defying expectations. The most tantalizing clue might lie in the bursts themselves. Unlike the chaotic splatter of other repeaters, this source's emissions during its active phase often arrive in tight clusters, suggesting an engine that doesn't just turn on, it revs up, accelerates, then winds down. That behavior mirrors terrestrial processes like earthquake swarms or volcanic activity, where stress builds and releases in waves. Perhaps the magnetar's crust, under unimaginable strain, fractures in predictable cycles, its magnetic field lines snapping and reconnecting in a cosmic drumbeat. Yet for all we've learned, the 16-day enigma only deepens the mystery. If magnetars are behind FRBs, why don't more exhibit such clockwork precision? Is this object uniquely ordered, or are others hiding their rhythms in plain sight? Their patterns too subtle or too long for us to detect yet, and perhaps most unsettling, what if this regularity isn't a quirk of physics but a signpost pointing toward phenomena we haven't even begun to imagine? FRB 180916 doesn't just challenge our theories, it whispers that the universe's rulebook might have chapters we've never even glimpsed. Among the countless mysteries wrapped up in fast radio bursts, few are as unsettling as the ones that seem to come from nowhere. Picture this: astronomers trace a burst's path across the cosmos, following its dispersion signature like breadcrumbs through interstellar space, only to arrive at empty darkness, no galaxy, no star cluster, just vast, yawning voids between the threads of the cosmic web. These are the FRBs without homes, signals that appear to originate in the loneliest places in the universe. And their existence throws everything we think we know about these bursts into question. Take FRB 190523, detected in 2019. When researchers pointed the Hubble Space Telescope toward its origin, expecting to find a distant galaxy, they found nothing. Not a single star, not even a wisp of interstellar gas. The burst had come from a region of space so empty it defied every expectation. If FRBs are born from extreme cosmic objects like magnetars or colliding neutron stars, things that form inside galaxies, how could one erupt from a place with no visible matter for millions of light years in any direction? This wasn't just a puzzle, it was a cosmic contradiction. The implications are staggering. Either these bursts can travel much farther from their sources than we thought, skimming along intergalactic magnetic fields like rogue waves, or their origins are far stranger than we've imagined. Some theorists suggest they might be the echoes of ancient cataclysms, events so violent they flung their remnants beyond the edges of galaxies. Others propose more exotic ideas, dark matter interactions, cosmic strings vibrating in the void, or even the evaporation of primordial black holes left over from the Big Bang. Each possibility stretches the boundaries of known physics, but the plot thickens. In 2022, another ghostly burst, FRB 211012, appeared to originate in a galaxy cluster's outskirts where few stars exist. The strangest part, its dispersion measure suggested it had traveled through significantly more gas than should be present in such an empty region. It's as if the signal passed through an invisible galaxy, one we can't see because it's made of something other than ordinary matter. Could there be dark galaxies lurking in these voids, their mass hidden but their influence detectable only when an FRB slices through them? The idea isn't as far-fetched as it sounds. Simulations show the universe should be dotted with these shadowy structures, their gravitational pull shaping the cosmic web even as they evade our telescopes. Then there's the timing problem. If FRBs born in voids are the aftermath of rare, catastrophic events like the collapse of invisible dark matter structures, why do some repeat? The laws of probability suggest we shouldn't catch multiple bursts from such desolate regions unless they're being generated continuously. That would require an engine that doesn't just exist in the void but thrives there, a perpetual cosmic battery humming in the dark. Perhaps the most unsettling possibility is that we're seeing the limits of our own technology. Some of these hostless bursts might actually come from galaxies so faint, so choked with dust, they're practically invisible at optical wavelength. Or their light could be redshifted beyond recognition, stretched by the expansion of the universe into obscurity. Even the mightiest telescopes have blind spots. But that explanation doesn't account for all the anomalies. There are too many bursts, too many precise localizations that point unequivocally to emptiness. These orphaned FRBs force us to confront a humbling truth. The universe is vast not just in space but in possibility. For every rule we've painstakingly pieced together about how cosmic objects behave, there's an exception waiting in the dark. The voids between galaxies aren't just empty stretches. They might be hiding entirely new classes of phenomena, echoes of physics operating in realms we've barely begun to explore. And every burst from nowhere is a whisper, reminding us that the map of the cosmos still has uncharted territories. So the next time an FRB flickers onto our screens, trailing no visible origin, don't think of it as a missing piece. Think of it as a signpost pointing toward the next great frontier of discovery. Because in the end, the most important thing these ghostly signals teach us isn't just where they come from, it's how much we still have left to find. Imagine a signal so powerful, it doesn't just travel across the universe, it twists. That's the bizarre reality of certain fast radio bursts that arrive with their radio waves spiraling like corkscrews, a phenomenon so extreme it shouldn't be possible. This isn't just random cosmic static. It's evidence that these bursts are punching through magnetic fields of unimaginable strength, fields that, according to everything we know about intergalactic space, simply shouldn't exist there. The detective work begins with something called Faraday rotation. When polarized radio waves pass through a magnetic field, their orientation subtly shifts a celestial fingerprint, revealing the hidden forces they've encountered. But in 2021, astronomers studying FRB 180301 observed something that defied all expectations. Its radio waves weren't just nudged, they were violently twisted, requiring passage through a magnetic field millions of times stronger than the diffuse gas between galaxies should allow. It's as if the signal had barreled through the cosmic equivalent of a particle accelerator's heart, emerging fundamentally altered. Where could such crushing magnetic fields hide? Intergalactic space is supposed to be the universe's quiet suburb, a near-perfect vacuum with magnetic fields so weak they're barely detectable. Yet this FRB's polarization suggests it traveled through a region where magnetic forces rival those near neutron stars. One possibility is that we're seeing echoes of an invisible cosmic architecture, vast magnetized filaments of gas threading between galaxies like unseen power lines. These structures, predicted by some simulations but never directly observed, could be remnants from the universe's infancy when plasma currents sculpted the first large-scale structures. Then there's the wild card scenario. What if the magnetism isn't in the space between galaxies at all? Some theorists argue these extreme Faraday rotations might originate much closer to the FRB source, in environments so extreme they warp the very fabric of electromagnetism. Picture a magnetar shrouded in a hypermagnetic nebula, a storm of plasma where magnetic field lines are braided tighter than steel cables, twisting every radio wave that escapes. Or perhaps we're witnessing the fingerprints of entirely new physics, domains where dark matter interacts unexpectedly with electromagnetic fields, or regions where quantum gravity effects amplify magnetism to preposterous levels. The implications ripple outward. If these magnetic monsters exist, they could rewrite our understanding of cosmic evolution. Magnetic fields play crucial roles in star formation, galaxy growth, and even the propagation of cosmic rays, but we've always assumed their influence was confined to galaxies' boundaries. Yet polarized FRBs suggest magnetic influence might stretch far beyond, invisibly shaping the universe's grandest scales. It's like discovering an entire hidden layer of cosmic weather, with storms raging where we thought only calm emptiness existed. What makes this enigma especially frustrating is that polarization measurements are maddeningly rare. Most FRB detections lack the precision to reveal these subtle twists, leaving us with only a handful of data points. But each new polarized burst adds another piece to the puzzle. Some show moderate rotation, others extreme, hinting that whatever's creating these fields isn't uniform. It's a cosmic patchwork of magnetic extremes scattered across the voids between galaxies. As telescopes grow more sensitive, this polarization mystery may hold the key to unlocking FRB's deepest secrets. These twisted signals aren't just messages about their sources, they're cosmic probes, revealing the invisible forces that shape the universe's emptiest realms. And with every new detection, we're forced to confront an unsettling truth. The space between galaxies isn't just empty. It's alive with hidden forces we're only beginning to comprehend. One of the most head-scratching behaviors in fast radio bursts isn't just their sudden appearance, it's their slow, deliberate fade. Picture a cosmic piano where each note plays slightly lower than the last, sliding down the scale in a ghostly glissando. That's precisely what astronomers observe in some repeating FRBs. A mysterious frequency drift where consecutive pulses arrive at incrementally lower radio frequencies, as if the source itself is winding down in real time. This isn't just random noise, it's a pattern so consistent it hints at fundamental physics playing out in ways we've never seen before. Take FRB 121102, the prolific repeater that's become a laboratory for FRB science. When researchers dissected its bursts, they noticed something peculiar. Within each active window, the first pulse might scream at 1,400 MHz, roughly the frequency of a microwave oven's hum. But the next would drop to 1,350, then 1,300. Like a record player gradually running out of power, the signal's pitch slides downward over hours or days, only to reset when the next activation cycle begins. This drift isn't unique to one source either. Multiple repeaters exhibit the same behavior, as if obeying some universal cosmic rulebook we haven't read. So what's dragging these frequencies down? One compelling theory points to the environment around magnetars, those ultramagnetic neutron stars thought to power many FRBs. Imagine the star shrouded in a roiling plasma fog. its magnetic field lines twisted like spaghetti. As a burst of radiation punches through this chaotic soup, higher frequency waves escape first, like sprinters dashing through an obstacle course. Lower frequencies, slowed by interactions with the plasma, lag behind, arriving moments later. But with each subsequent burst, the magnetar's fury might heat and ionize the surrounding plasma even more, thickening the fog. Now the next burst must plow through denser resistance, forcing its higher frequencies to dampen while the lower ones persist, creating the illusion of a downward drift. Another possibility takes us into the heart of the magnetar itself. These stellar corpses are thought to harbor crusts of crystalline neutrons under unimaginable pressure, able to fracture like tectonic plates. A starquake could send shockwaves rippling through the magnetar's interior, momentarily altering its magnetic field geometry. As the field relaxes back to equilibrium, the frequency of emitted radiation might naturally decay, like a guitar string loosening its tension. Each aftershock would tweak the field further, producing bursts that step down the cosmic keyboard, but the plot thickens. Some FRBs show drift rates that math says shouldn't align with known plasma physics. The shifts are too smooth, too predictable, as if guided by an unseen hand. That's led to wilder speculations. Could these be echoes of light bending around a rotating black hole's ergosphere, where spacetime itself drags like molasses? Or signatures of collapsing, strange matter, a hypothetical state where neutrons dissolve into quark soup? Even more unsettling is the notion that we're seeing Doppler shifts from a source accelerating away from us at relativistic speeds, though no known object can both survive such motion and produce coherent radio waves. The true answer might lie in a blend of these ideas or none of them. What makes the drift so tantalizing is its consistency. It's not random noise, it's a fingerprint. If we can decode why these cosmic sirens always slide downward, we might unlock secrets about the densest matter in the universe, the structure of magnetic fields in extreme environments, or even new states of physics that only reveal themselves under conditions no lab on Earth could replicate. For now, the downward drift remains one of FRB's most stubborn puzzles. It's a reminder that these signals aren't just blips in the void. They're intricate narratives. Each frequency shifts a sentence in a story we're only beginning to translate. And like any good mystery, the closer we look, the deeper the questions become. The numbers alone defy belief. A fast radio burst unleashes more energy in milliseconds than our sun emits in decades. Some clock in at 500 million times the sun's luminosity, packing enough punch to briefly outshine entire galaxies. How does something so fleeting produce such staggering power? The answer lies in physics pushed to its breaking point, where the ordinary laws governing energy and matter no longer apply. Let's break it down. If you compressed all the sunlight that strikes Earth over 90 years into a single snap of your fingers, you'd still fall short of an average FRB's output. That energy isn't just radiated aimlessly, it's focused into a laser-like beam narrower than a pencil's width, amplifying its brightness to detectable levels across billions of light years. But this extreme efficiency only deepens the mystery. Even cosmic heavyweights like supermassive black holes or colliding neutron stars struggle to explain such precise, concentrated fury. One leading contender, magnetars, especially during their apocalyptic starquakes. Picture a neutron star's crust, denser than diamond, cracking under magnetic pressures a quadrillion times Earth's field. When these fractures occur, they release pent-up energy like a coiled spring snapping, vibrating magnetic field lines so violently, they convert motion into radio waves with near-perfect efficiency. It's akin to plucking a guitar string made of pure spacetime, where each oscillation generates a pulse bright enough to pierce the cosmic dark. Yet magnetars might not be the only players. Some theorists propose synchrotron masers, shock waves from collapsing neutron stars or black hole jets interacting with surrounding plasma to create natural amplifiers. Imagine a cosmic feedback loop. particles accelerated to near-light-speed spiral around magnetic fields, emitting radiation that stimulates more emission, cascading into a brief but monstrous burst. This could explain why some FRBs seem to originate in chaotic stellar nurseries, where raw materials for such fireworks abound. Then there's the wildcard blitzars. Hypothetical supermassive neutron stars spinning so fast they're nearly black holes might delay their inevitable collapse thanks to centrifugal force. But when rotation finally slows, the star would implode in a final, catastrophic burst, releasing its entire remaining energy in one radio scream. It's a cosmic last gasp scenario where the death throes of an impossible object briefly light up the universe. But the paradox deepens. If FRBs are this energetic, why don't we see other signatures, gamma rays, X-rays, or afterglows? Some bursts arrive suspiciously clean, lacking the expected counterparts. This silence hints that FRB engines might be even more efficient than we've imagined, channeling nearly all their energy into radio frequencies alone. Or perhaps we're missing an entire class of emissions signals so exotic, our telescopes aren't equipped to catch them, the most humbling realization. However FRBs do it, they're breaking records we didn't know existed. They're proof that the universe has energy factories beyond our wildest theories, objects or processes that take everything we know about physics and twist it into something unrecognizable. And with every new detection, we're forced to ask, if this is possible, what else are we getting wrong? When a supernova explodes or neutron stars collide, they leave behind glowing wreckage, an afterglow that can linger for weeks, even years, giving astronomers precious time to study the aftermath. But fast radio bursts, they vanish without a trace, no lingering heat, no fading light, just a sudden, brilliant scream of radio waves, then silence. This absence of afterglow isn't just inconvenient, it's a fundamental puzzle that challenges our understanding of how these bursts work and why they're so different from every other energetic phenomenon in the cosmos. Take gamma-ray bursts, for example. These colossal explosions, often marking the birth of black holes, flood space with high-energy radiation that gradually fades across multiple wavelengths. Telescopes can track their remnants for months, piecing together what happened. Even magnetar flares, those violent outbursts from ultramagnetic neutron stars, leave behind X-ray echoes that hint at their origins. But FRB, aside from a handful of exceptions, they're cosmic ghosts. One moment they're there, flooding detectors with energy, the next to nothing. It's as if whatever produces them switches on with unimaginable power, then disappears back into the void without disturbing a single atom. This missing afterglow points to something crucial. FRBs must be incredibly clean events. Most cosmic explosions are messy affairs, spewing debris and radiation in all directions. But FRBs seem to channel nearly all their energy into a narrowly focused beam of radio waves, with almost nothing leaking out as heat or light. Imagine the difference between a bomb blast scattering shrapnel and shockwaves in every direction, and a precision laser cutter leaving no scorch marks behind. That level of efficiency defies most known astrophysical processes. Even the most extreme objects we know, like magnetars, should produce some collateral emission when they unleash such monstrous energy. So where does all that energy go? One possibility is that FRB sources are surrounded by environments so dense, any afterglow gets smothered before it can escape. Picture a magnetar buried in a thick cocoon of plasma. Its radio beams might punch through like needles while other wavelengths get absorbed completely. Alternatively, the bursts might originate in regions where particles are already accelerated to near light speeds, meaning there's no leftover energy to dissipate as an afterglow. It's like a sprinter crossing the finish line and evaporating mid-stride, no cool down, no deceleration, just instant disappearance. The rare exceptions only deepen the mystery. A few FRBs, like the Milky Way's homegrown burst from magnetar SGR 1935 + 2154, have been linked to X-ray counterparts. Others show faint, persistent radio sources at their locations, hinting at ongoing activity. But these are the outliers. The vast majority leave no footprint, suggesting that whatever's producing them operates on principles we haven't yet imagined. Could they be tapping into exotic physics like quantum vacuum decays or space-time singularities that don't produce conventional afterglows? Or are we simply missing the afterglow's true signature, hidden in wavelengths or timescales we're not equipped to detect? The absence of afterglow isn't just an observational headache, it's a clue. It tells us FRBs are fundamentally different from anything else in our cosmic zoo. They're not just louder versions of known phenomena, they're something entirely new, operating by rules we're still struggling to decode. And until we understand why they leave so little trace, these bursts will remain some of the most elusive and tantalizing enigmas in the universe. Deep in the cosmic static, some fast radio bursts carry an eerie secret. They arrive not once, but multiple times, like echoes bouncing between unseen walls. This isn't just random interference. These bursts have been caught in an interstellar hall of mirrors, their signals splitting into identical copies that reach Earth seconds or even minutes apart. The culprit, vast, invisible clouds of plasma floating between galaxies, acting like cosmic reflectors that warp and duplicate the signals passing through them. One of the most striking examples came from FRB 121102, the prolific repeater that never stops surprising astronomers. In 2019, researchers noticed something bizarre. Certain bursts from this source arrived with faint but unmistakable twins, delayed by tiny fractions of a second. The explanation was as elegant as it was mind-bending. Somewhere along its 3 billion light-year journey, the signal had grazed a dense knot of ionized gas, possibly the remnants of an ancient supernova or a turbulent stellar nursery. As the radio waves plowed through this plasma curtain, part of the signal scattered backward, then forward again, creating an echo effect akin to shouting into a canyon and hearing your voice bounce off distant cliffs. But here's where physics gets weird. Unlike sound waves, which slow down when reflecting off surfaces, light, and thus radio waves, travels at a constant speed in a vacuum. So how can echoes arrive later without breaking the cosmic speed limit? The answer lies in the tortuous path these echoes take. While the main burst barrels straight through intergalactic space, its echo might ricochet off multiple plasma clouds, zigzagging across millions of light-years before finally reaching us. Each detour adds delay, stretching the signal like taffy. In extreme cases, these detours can even alter the burst's dispersion measure, fooling astronomers into thinking they've detected an entirely new FRB when it's just the same one, reflected and reshaped by the cosmos itself. These plasma mirrors aren't just passive bystanders. Their density and magnetic fields imprint hidden details onto the echoes like forensic fingerprints. By studying the delay between primary bursts and their reflections, astronomers can map the invisible structures lurking between galaxies, structures too diffuse to see directly, but whose presence warps passing signals. Some of these plasma clouds might be remnants of long-dead stars ejected during supernova and now drifting in the void. Others could be filaments of the cosmic web, the sprawling network of gas that connects all galaxies in the universe. Each echo is a fleeting snapshot of this hidden architecture, revealing where ordinary telescopes see only darkness. Yet the echoes also raise new questions. Why do some FRBs produce them while others don't? Is it pure chance, a matter of alignment between burst, plasma cloud, and Earth? Or do certain FRB engines create environments more prone to reflection? And could some of the one-off bursts we've catalogued actually be echoes of much older events, their origins hopelessly obscured by cosmic scattering? The most tantalizing possibility is that echoes might help solve FRB's greatest mystery, pinpointing their exact sources. If we can trace the path of a reflected signal backward, like following a laser beam's ricochet, we might finally zoom in on the chaotic neighborhoods where these bursts are born. For now, every echoed FRB is a gift, a chance to peer deeper into the universe's shadowy corridors. They remind us that space isn't empty. It's a labyrinth of invisible walls and barriers, bending and twisting signals in ways we're only beginning to understand. And with each echo, we're not just hearing a burst, we're hearing the universe's hidden geometry whisper back. Among the most baffling behaviors of fast radio bursts are those that don't just repeat, they tick like celestial clocks, bursting at intervals so precise they rival atomic timekeeping. This isn't the erratic flickering of a dying star. It's rhythmic, calculated, almost mechanical, and it's forcing astronomers to confront an electrifying possibility that some FRBs might be cosmic pendulums, their bursts governed by the precise dance of orbital mechanics or the wobble of spinning stellar corpses. Take FRB 180916, the 16-day metronome we've already met. Its predictability is so exact you could plot its active phases on a calendar. But it's not alone. Other sources like FRB 121102 follow similarly regimented schedules, albeit with longer cycles, 157 days of silence, then a flurry of activity. Over and over, these patterns scream structure, hinting at forces far more organized than the chaotic explosions we typically associate with neutron stars or black holes. The leading theory points to binary system celestial pairs locked in gravitational embraces. Picture a magnetar orbiting another dense object, perhaps a black hole or massive star. As the magnetar swings close, tidal forces or bursts of stellar wind could trigger eruptions like clockwork. The inactive period, that's the magnetar retreating to the far side of its orbit, its radio beams now pointed away from Earth. It's a compelling idea, but there's a catch. No known binary system behaves quite like this. The timing is too precise, the bursts too consistent. Then there's precession, the slow wobble of a spinning object's axis. Magnetars, with their incomprehensibly strong magnetic fields, don't rotate smoothly. Their crusts can warp under magnetic strain, causing their poles to trace lazy circles in space. If those poles beam radiation like lighthouse lamps, they might sweep across Earth's line of sight at predictable intervals, creating the illusion of an on-off switch. But precession is usually messier, less rigid, and why 16 days, why 157? The numbers feel arbitrary, untethered from known astrophysical processes. The wild card, these patterns might be evidence of something entirely new. Cosmic strings, hypothetical defects in space-time left over from the Big Bang could vibrate at set frequencies, producing bursts like plucked guitar strings. Or perhaps we're seeing the death throes of strange stars, hypothetical objects made of quark-gluon plasma. Their collapse is timed to quantum resonances we don't yet understand. The most tantalizing clue lies in the details. Some periodic FRBs don't just turn on and off. Their bursts cluster in tight windows during active phases, then vanish completely. This suggests the underlying engine isn't just cycling, it's winding up, releasing pent-up energy in waves before resetting. Its behavior more akin to geysers than explosions, where pressure builds until it can't be contained. What makes these periodic bursts so maddening and so thrilling is their refusal to fit neatly into any existing box. They defy the chaos we expect from the universe's most violent objects, offering instead a precision that feels almost artificial. But therein lies the beauty. Whether from orbits, wobbles, or physics we've yet to discover, these cosmic timekeepers are rewriting the rules, one tick at a time. Every cosmic signal has its comfort zone, a sweet spot where it shines brightest. For fast radio bursts, that should be the lower end of the radio spectrum. Yet when astronomers point their telescopes toward frequencies below 400 MHz, expecting a cacophony of bursts, they're met with near silence. It's as if something in the universe is tuning out these cosmic broadcasts before they reach us, and the implications are rewriting what we thought we knew about interstellar space. The mystery begins with basic physics. Low-frequency radio waves, those gentle ripples longer than a human hand, are incredibly resilient. Unlike their high-frequency cousins, which scatter easily, these radio waves can travel vast cosmic distances with minimal distortion. That's why AM radio stations sometimes crackle to life unexpectedly hundreds of miles away at night, their signals bouncing off Earth's ionosphere. Given that resilience, the cosmos should be teeming with low-frequency FRBs. But it isn't. Detectors like the Murchison Widefield Array in Australia, tuned to hunt for bursts between 70 and 300 MHz, catch only a fraction of the expected number. And when they do, the signals often arrive looking like they've been through a cosmic meat grinder, stretched, smeared, and barely recognizable. So where are all the missing bursts? One clue lies in the soup of electrons floating between galaxies. While space is mostly a vacuum, it's not entirely empty. Thin clouds of ionized gas plasma permeate the cosmic web. When radio waves pass through this plasma, they interact with free electrons, slowing down slightly. Lower frequencies feel this drag more intensely, like wading through thicker mud. If the plasma is dense enough, it can scatter or even absorb these waves entirely, especially if they're traveling from the early universe where the intergalactic medium was far more crowded. But here's the twist: even accounting for known plasma densities, too many low-frequency FRBs are vanishing. That suggests something else is at play, perhaps a hidden population of ultra-diffuse plasma clouds too faint to detect directly. These stealthy structures might lurk along the filaments of the cosmic web, their presence revealed only when they selectively mute passing radio signals. Or the answer could lie in the environments around FRB sources themselves. Magnetars, for instance, are often cocooned in hypermagnetic nebulae, storms of charged particles that might filter out low frequencies before they ever escape into intergalactic space. The plot thickens when you consider how low-frequency FRBs behave when we do catch them. Many appear scintillated, their signals flickering like stars viewed through Earth's turbulent atmosphere. This suggests they've passed through turbulent plasma screens, regions where density variations act like frosted glass, diffusing the light. Some bursts even exhibit bandwidth depolarization, where their polarization unravels at lower frequencies, as if the waves have been twisted by magnetic fields along their journey. Together, these fingerprints point to a universe far clumpier and more magnetized than our current maps show. Then there's the most tantalizing possibility. We might be witnessing a breakdown in our understanding of radio wave propagation itself. Quantum mechanics predicts that photons should interact minimally with the sparse particles of intergalactic space, but what if conditions near FRBs are so extreme they bend those rules? Theories like vacuum birefringence, where space itself behaves like a prism under intense magnetic fields, could selectively filter certain frequencies. Or perhaps plasma waves in the FRB's immediate vicinity are reshaping the signal, the same way crashing surf distorts a shout carried on the wind. The absence of low-frequency FRBs isn't just an observational headache, it's a treasure map. Every missing burst hints at invisible structures hiding between galaxies. Every smeared signal carries clues about the turbulent, magnetized highways spanning the cosmos. And as telescopes push into ever lower frequencies, we're not just hunting for bursts. We're decoding the universe's hidden ledger, written in static and silence. So the next time an FRB flickers to life at 800 MHz but leaves its lower frequency counterpart conspicuously absent, don't think of it as a gap in the data. Think of it as a cosmic whisper revealing everything we can't see until now. When a star explodes as a supernova, it doesn't just vanish, it leaves behind a cosmic crime scene, glowing for years with clues about its violent end. So when astronomers noticed some fast radio bursts appearing suspiciously close to the aftermath of these stellar explosions, it sparked a heated debate. Could FRBs be the hidden aftermath of supernova, screaming into the void long after the initial blast? The idea isn't as far-fetched as it sounds, but the evidence is far from clear. Take FRB 201906A, detected in 2019. When telescopes swiveled toward its origin, they found something unexpected, not just a distant galaxy, but one still reeling from a supernova that had lit up the same spot just a few years earlier. The timing was too close to ignore. Could the burst have been triggered by the collapsing core of the dead star, or perhaps by a newborn magnetar left spinning in the wreckage? The scenario makes intuitive sense. Supernovae unleash unimaginable energy, and their remnants, especially neutron stars, are known to produce intense magnetic fields. If a magnetar formed in the chaos, its apocalyptic tantrums might explain both the FRB's power and its location. But here's where the plot thickens. Not every FRB sits near a supernova remnant, and not every supernova produces detectable bursts. In fact, most don't. That inconsistency has led skeptics to argue the connection might be pure coincidence, a cosmic game of chance where two rare events occasionally overlap. After all, massive stars explode all the time, and with FRBs now being detected by the hundreds, some statistical overlap is inevitable. The real question isn't whether they can occur together, but whether one causes the other. Proponents of the link point to tantalizing details. Some repeating FRBs, like 121102, originate in star-forming regions where supernovae are frequent. These stellar nurseries are littered with the corpses of dead stars, many of them magnetars, and when astronomers model the aftermath of a supernova, they find conditions ripe for FRB production: collapsing magnetic fields, turbulent plasma, and shocks that could accelerate particles to extreme energies. It's a perfect storm of physics, at least on paper, yet critics counter with a glaring hole in the theory: timescales. Supernova remnants fade over centuries, but the magnetars within them should remain active for thousands of years. If FRBs are tied to these objects, why don't we see more bursts from older remnants? Why do some FRBs appear in galaxies with no recent supernova at all? The math gets even murkier when you consider that the most energetic FRBs dwarf even the power of a supernova's initial blast. How could a stellar corpse produce something more violent than the explosion that created it? The debate takes a stranger turn when you consider alternative explanations. Some theorists suggest FRBs might not come from the supernova's aftermath at all, but from its prelude. In the final moments before a massive star collapses, its core can spin feverishly, twisting magnetic fields into knots. If those fields snap just before the explosion, they might unleash a proto-FRB, a final scream before the lights go out. Others propose that FRBs could be sparked when a supernova's shockwave slams into dense clouds of surrounding gas, creating particle acceleration on a cosmic scale. What makes this mystery so compelling isn't just the science, it's the stakes. If even a fraction of FRBs are linked to supernova, it would revolutionize how we understand stellar death. These bursts could become early warning systems, signaling the birth of magnetars or the collapse of stars too distant to see. But until the evidence tips decisively in one direction, the FRB supernova connection remains one of astrophysics' most tantalizing maybes, a cosmic what-if written in radio waves and stardust. Right now, as telescopes scan the skies for fast radio bursts, there's an unsettling possibility lurking beneath every detection. What if we're only catching the stragglers? Imagine standing in a dark field, watching fireflies blink in the distance. You might count a dozen, but in reality, thousands could be flashing all around you, their light aimed away from your eyes. That's the essence of the dark FRB hypothesis, a growing realization that the bursts we detect might represent just a sliver of an invisible storm raging across the cosmos. The math is sobering. FRBs emit their energy in narrow beams like interstellar laser pointers. If those beams aren't pointed directly at Earth, they slip past unnoticed. Given how few we've detected compared to estimates of their true occurrence rate, some calculations suggest we might be missing 99.9% of all FRBs. That's not just a sampling error. It's like trying to study ocean life by dipping a teaspoon into the sea. This beam effect isn't just theoretical. We've seen it play out with pulsars, those cosmic lighthouses that only become visible when their spinning beams sweep across our line of sight. But with FRBs, the challenge is even greater. Pulsars rotate predictably, their beams sweeping like clockwork. FRB, their beaming could be chaotic. Some might flare once and never realign, while others, like the repeating FRB 121102, might have wider beams that periodically glance our way. The implications are staggering. If most FRBs are indeed shooting into the cosmic void undetected, their true energy output could dwarf current estimates. A burst that seems like a once-in-a-lifetime event from our perspective might actually be commonplace elsewhere in the universe. This also complicates efforts to pin down their origins. A galaxy that appears to host just one FRB might actually harbor hundreds, their signals spraying in all directions like water from a spinning garden hose. There's another layer to this cosmic hide-and-seek. Even the bursts we do catch might be distorted versions of their true selves. Signals beamed at oblique angles could pass through more interstellar gas before reaching us, stretching and twisting their profiles. That means some unique FRBs might actually be garden-variety bursts viewed from unlucky angles, their strangeness an illusion of geometry rather than physics. The dark FRB hypothesis forces us to confront a humbling truth. We're not just decoding these signals, we're decoding the ones that happen to reach us. The universe might be crackling with FRBs in frequencies we can't detect, from directions we can't see, at energies we can barely fathom. And until we build telescopes capable of catching these wayward beams, or stumble upon a burst so powerful it's visible from any angle, we're left peering through a keyhole, guessing at the storm beyond the door. Some fast radio bursts don't just scream into the void, they sing. Imagine tuning a radio dial and catching not a single blast of static, but a cascading chorus of subbursts, each dancing across the frequencies like notes in a cosmic symphony. This is the bizarre reality of what astronomers call the FRB forest, signals so structurally complex. They reveal layers of hidden physics happening in the blink of a cosmic eye. The first hints emerged in 2017, when researchers studying the repeating FRB 121102 noticed something strange. Its bursts weren't monolithic pulses. Instead, they fractured into multiple subcomponents, sometimes spaced milliseconds apart, each tracing a distinct path down the radio spectrum. It was as if the source wasn't just exploding once, but conducting an intricate series of microscopic detonations, each with its own energy fingerprint. Then came FRB 190523b, whose signal resembled a falling arpeggio, higher frequencies arriving first, followed by lower ones in a staggered descent. These weren't anomalies, they were blueprints hinting at machinery far more sophisticated than anything we'd imagined. What could possibly produce such intricate patterns? One leading theory points to magnetars wrapped in superheated plasma tornadoes. Picture a neutron star's magnetic field lines twisting like rubber bands until they snap, releasing energy not in one clean break, but in a cascade of smaller reconnections. Each twang of a magnetic field line could generate a subburst, with the overall structure reflecting the chaotic choreography of the star's crust quakes. Alternatively, the bursts might be slicing through dense plasma clouds near their source, scattering like light through a prism, lower frequencies lagging behind as they battle the turbulent soup. But the forest phenomenon gets even weirder. Some FRBs show frequency drifting, where later subbursts appear at systematically lower frequencies than earlier ones, like a pianist sliding their hand down the keys. This can't be explained by simple scattering. It suggests the emission mechanism itself is evolving in real time, perhaps a magnetar's flare decaying in energy, or a shockwave plowing through ever denser layers of stellar debris. Then there's the sad trombone effect seen in FRB 180301, where sub-bursts not only drift downward in frequency but also slow down, their spacing stretching like time itself is winding down. The most mind-bending possibility, these intricate structures might be clues to quantum-scale physics playing out on cosmic scales. Some models suggest FRB sub-bursts could arise from superradiance, a phenomenon where atoms in extreme magnetic fields synchronize their emissions like a choir finding harmony. Others speculate about spark storms in neutron star magnetospheres, where dense packs of charged particles erupt in fractal-like chains, each spark birthing another. Even string theory gets a nod, with hypothetical cosmic strings vibrating at multiple harmonics as they snap. Yet for all their complexity, these FRB forests offer a rare gift: resolution. Like zooming in on a fingerprint, their substructures let astronomers probe the nanosecond physics of environments we'll never visit. Every drifting sub-burst maps the turbulent plasma between galaxies. Every microsecond delay traces the warp and weft of magnetic fields stronger than anything on Earth. And with new telescopes like the Deep Synoptic Array coming online capable of dissecting FRBs with unprecedented precision, we're not just hearing the universe's whispers anymore. We're learning to decipher its poetry, so the next time an FRB flickers to life, remember, what looks like a blip on a screen might be a universe of physics folded into milliseconds. The forest isn't just noise, it's a message written in the only language the cosmos knows, and we're just beginning to learn how to read. If fast radio bursts are as common as the distant universe suggests, our cosmic neighborhood should be teeming with them. The Milky Way sits in a modest galactic commune, the local group, a gathering of about 80 galaxies sprinkled across 10 million light-years. Given how frequently we spot FRBs from billions of light-years away, logic says we should catch dozens from next door. Yet the tally stands at 1, a single confirmed burst from inside our galaxy, while the rest remain frustratingly out of reach. This scarcity isn't just odd, it's a clue, hinting that FRBs might not be the universal phenomenon we've assumed. First, consider the detection bias. The farther away an FRB is, the more intergalactic material its signal plows through, stretching its dispersion measure into unmistakable territory. Local group bursts, by contrast, traverse so little gas that their dispersion is minuscule, easy to mistake for terrestrial interference or a glitch. It's like trying to hear a whisper in a quiet room when you're used to identifying shouts from miles away. Even our homegrown FRB, the Magnetar SGR 1935+2154, was only recognized because it arrived with an X-ray flare, a cosmic breadcrumb trail leading back to its origin. Without that counterpart, it might have been dismissed as satellite noise, but the plot thickens. If local group galaxies host FRB sources similar to those in the distant universe magnetars, for instance, why aren't they producing bursts at the same dizzying rate? The answer might lie in age. Distant FRBs often trace back to young, chaotic galaxies where stars form and die violently, creating ideal nurseries for magnetars. The local group, by contrast, is a retirement community. Its galaxies are quieter, their star-forming heyday billions of years behind them. Fewer newborn magnetars mean fewer bursts, a cosmic demographic quirk that leaves our neck of the woods eerily silent. Then there's the luminosity problem. The FRBs we detect from across the universe are monsters, their energy amplified by distance. To be visible across such gulfs, they must be exceptionally bright, perhaps far brighter than whatever typical, quieter bursts might exist locally. If local group FRBs are gentler, their whispers might simply fade into the background hum of the cosmos, undetectable by current telescopes. It's like living next to a fireworks factory, but only noticing the distant displays that light up the horizon, missing the smaller sparks close to home. The most tantalizing possibility, FRBs might need extreme environments to thrive, conditions rare in our local group. distant bursts often originate in galaxies with frenetic star formation, thick plasma, and turbulent magnetic fields. These are pressure cookers for cosmic physics where magnetars can be wound tighter, their magnetic fields twisted to breaking point. Our galactic neighbors, by comparison, are lukewarm ponds. Without those extreme conditions, perhaps potential FRB sources here simply fizzle instead of igniting. This scarcity isn't just frustration, it's opportunity. Every undetected local group FRB forces us to refine our theories, to ask whether we've misunderstood these bursts entirely. Are we mistaking the loudest, rarest examples for the norm, or is the universe hiding an entire population of stealth FRBs, their signals too subtle or infrequent for our current tools? The answer might require telescopes 10 times more sensitive, or a complete rethinking of where and how we search. Until then, the silence next door remains one of astrophysics' most provocative puzzles. Picture a cosmic lighthouse, not one made of brick and glass, but forged from the corpse of a dead star, spinning faster than a kitchen blender and wrapped in magnetic fields so intense they could atomize matter from thousands of miles away. This is the heart of the leading explanation for fast radio bursts. Magnetars, the universe's most volatile neutron stars, firing beams of radio waves across the cosmos like a spinning beacon in the void. At first glance, the lighthouse model seems elegant. Magnetars are already cosmic extremes, neutron stars with magnetic fields a quadrillion times stronger than Earth. When their crusts crack under magnetic strain, these starquakes can unleash energy equivalent to a solar flare compressed into milliseconds, vibrating magnetic field lines like plucked guitar strings. Those vibrations convert motion into radio waves, which then jet outward along the star's magnetic poles. If those poles wobble as the star spins like a flickering lighthouse beam sweeping past a ship, Earth might catch fleeting glimpses of the resulting FRBs. The theory gained credence in 2020 when a Milky Way magnetar named SGR 1935+2154 erupted with an FRB-like burst just 30,000 light-years away. Here at last was smoking gun evidence linking these enigmatic signals to magnetar activity, but the devil's in the details, and the lighthouse model faces stormy seas when scrutinized. First, there's the sheer energy problem. While galactic magnetars like SGR 1935 produce impressive bursts, they're still orders of magnitude weaker than the most luminous cosmological FRBs. To explain those distant monsters, magnetars would need to operate at energy levels pushing the boundaries of physics, either through hyperactive tantrums we've never witnessed locally, or by inhabiting environments that amplify their emissions, like the dense plasma cocoons of young stellar nurseries. Then there's the clockwork precision of some repeating FRBs. Magnetars are notoriously chaotic, their rotations slow unpredictably, their magnetic fields tangle like spaghetti, yet sources like FRB 180916 burst with metronomic regularity every 16 days. No known magnetar behaves this predictably unless it's locked in a gravitational dance with a companion object, a scenario that raises its own questions. Why don't we see more binary-induced periodicity? And how do these systems survive the violent feedback of repeated FRBs without tearing apart? Perhaps the biggest wrench in the lighthouse mechanism is beam geometry. FRBs detected from across the universe must be incredibly narrowly focused, less than a degree wide, to appear as bright as they do. But magnetar emission models suggest their radio beams should fan out more broadly. That means either we're astronomically lucky to catch the rare edge of these beams, or something plasma lensing, magnetic funneling, is collimating the emission far more tightly than physics predicts. The lighthouse model isn't sunk yet. Tweaks like supernova fallback, where a newborn magnetar is swaddled in debris that focuses its beams, could resolve some discrepancies. Others propose that FRBs might arise from magnetars plunging through asteroid belts or accreting material from stellar companions, adding fresh fuel to the fire. But with every new burst that defies expectations, the cosmos reminds us, even its best understood monsters still guard their deepest secrets. The moment you mention a mysterious cosmic signal repeating at precise intervals, it's inevitable someone will ask, could this be aliens? Fast radio bursts with their mind-bending energy and bizarre patterns have sparked their fair share of extraterrestrial speculation. From headlines whispering about interstellar beacons to papers earnestly discussing ultra-advanced civilizations, the idea that FRBs might be deliberate messages or even byproducts of alien technology has lingered at the fringes of the conversation. But before we picture distant engineers aiming radio transmitters at Earth, let's dissect why the scientific community remains skeptical and what these bursts actually tell us about the universe. First, consider the raw physics. The energy requirements for an artificial FRB would beg a belief. Even harnessing the total output of a star like our Sun, a hypothetical Dyson sphere, wouldn't easily account for the millisecond-scale power spikes we observe. To focus that energy into a tight beam visible across billions of light years would demand engineering far beyond anything our laws of physics permit. And why would an advanced civilization waste such colossal resources on a signal that vanishes almost instantly with no obvious encoded information? Natural cosmic events, by contrast, routinely generate staggering energies through processes like magnetic reconnection or gravitational collapse. No aliens required. Then there's the cosmic distribution problem. FRBs come from everywhere: young galaxies, old galaxies, even the voids between them. If these were deliberate broadcasts, why scatter them so indiscriminately? An intelligent signal would presumably target star systems with potential listeners, not empty intergalactic space. Worse, the burst's dispersion measures their telltale fingerprints of traversing intergalactic gas, match perfectly with natural propagation through the cosmos. A synthetic signal would need to mimic this dispersion artificially, an absurdly convoluted choice for a species presumably trying to communicate efficiently. The repetition patterns, often cited as evidence of artificial design, also crumble under scrutiny. While some FRBs cycle with clockwork precision, their intervals 16 days, 157 days, don't correspond to any obvious mathematical constants or symbolic sequences. Natural orbital mechanics, like a magnetar circling a companion star, explain these timelines far more elegantly. Even the infamous WOW signal, a one-off radio blip often hailed as the best candidate for extraterrestrial contact, pales next to FRB's sheer abundance. With hundreds detected and more flooding in weekly, Occam's razor favors a natural explanation. That's not to dismiss the alien hypothesis outright. Science thrives on considering even the fringe ideas, then rigorously testing them. Researchers have hunted for signs of encoding in FRB patterns, searching for prime number sequences or other hallmarks of intelligence. So far, nothing. Meanwhile, the natural explanations keep gaining traction: magnetar outbursts, plasma lensing, even cosmic string vibrations. Each fits the data without invoking unfathomable alien megaprojects. Here's the irony: FRBs are evidence of intelligence, just not the kind we imagined. They're proof of the universe's boundless creativity, crafting phenomena we're only beginning to comprehend. The real mystery isn't whether aliens are phoning us, it's why nature keeps inventing ways to scream in radio waves we never knew existed. And that discovery, free of little green men, is far more thrilling. Some fast radio bursts don't just repeat, they erupt in frenzied clusters, like cosmic strings of holiday lights flickering to life all at once before plunging back into darkness. Astronomers call it the Christmas tree effect, and it's one of the most perplexing behaviors in the FRB playbook. Picture a source that sleeps soundly for weeks or months, then suddenly wakes in a hyperactive frenzy, firing off dozens of bursts in quick succession, sometimes mere seconds apart, before shutting off again as abruptly as it began. This isn't just repetition, it's cosmic binge-watching, with the universe blasting through an entire season of bursts in one sitting. The poster child for this phenomenon is FRB 121102, the repeater that never stops surprising scientists. During its active phases, this source doesn't drizzle bursts, it deluges them. Researchers have caught it spitting out over 100 flares in a single hour, each packing the energy of 100 million suns. Then, without warning, the faucet turns off. The silence that follows can last for months, a hiatus so complete it's as if the source vanishes from existence. What makes these clustered outbursts so baffling is their defiance of known astrophysical rhythms. Neutron stars, magnetars, and other exotic objects tend to follow predictable decay patterns, like a glowing coal cooling after a fire. But Christmas tree FRBs operate more like geysers, building pressure until they can't contain it, then erupting in a chaotic spray before resetting. The closest terrestrial analogy might be earthquake swarms, where tectonic stress releases in bursts rather than one massive quake. Yet even that comparison falls short when applied to objects with the mass of a sun crammed into a city block. One theory suggests these clusters arise from magnetars trapped in cosmic traffic jams. Imagine a neutron star's crust under unimaginable magnetic strain, fracturing not in one clean break but in a cascade of micro-snaps. Each fracture realigns the star's magnetic field slightly, triggering another burst until the system finally stabilizes. Alternatively, the bursts could be tapping into an external reservoir, perhaps a debris disk or a stellar companion, with material falling onto the magnetar in clumps, igniting fresh flares with each new bite. Then there's the wild card. What if these clusters aren't coming from one object at all? Some models propose that Christmas tree FRBs might actually be cosmic mirages, signals from multiple magnetars in a dense cluster, their bursts overlapping as they sweep past Earth like a parade of lighthouses. It's a controversial idea, but it could explain why some active windows seem to contain distinct families of bursts with subtly different characteristics. The real challenge lies in the pauses. Why do these sources go radio silent for such exact intervals? FRB 121102, for instance, follows a 157-day cycle with eerie precision. One possibility is that the quiescent periods are recovery phases, times when the magnetar's magnetic field rebuilds its strength after being drained by the outburst. Another suggests these pauses are geometric, the result of precession or orbital motion periodically tilting the burst beam away from Earth. Whatever the cause, the Christmas tree effect forces us to confront a universe far more dynamic than we imagined. These aren't steady cosmic engines humming along at predictable rates. They're capricious, temperamental, and prone to fits of extravagance followed by sullen silences. And with every new cluster detected, we're reminded, the cosmos doesn't just operate on grand scales of time and space. It thrives in the explosive, the episodic, and the gloriously unpredictable. When fast radio bursts erupt across the cosmos, they don't arrive alone, or at least they shouldn't. In a universe where cataclysmic events often announce themselves through multiple cosmic messengers, gravitational ripples, neutrino showers, X-ray flashes, FRBs stand out not just for their brilliance but for their puzzling solitude. Despite years of searching, astronomers have found almost no evidence of gravitational waves, neutrinos, or other high-energy signals arriving in lockstep with these bursts. It's as if the universe is throwing the most energetic tantrums imaginable, but forgetting to scream in anything but radio waves. Take gravitational waves, the space-time wrinkles generated by massive accelerating objects. When neutron stars collide, one of the early leading theories for FRB origins, they should send ripples through the fabric of reality detectable by observatories like LIGO and Virgo. Yet in every case where FRBs and gravitational wave detectors were observing the same patch of sky simultaneously, the result has been the same: silence. not so much as a whisper of space-time distortion to accompany the radio fireworks. This absence is especially baffling for repeating FRBs, which by definition imply an object surviving its own outburst. If these sources were catastrophic mergers, they'd be one-time events, not cosmic repeat offenders. Neutrinos, those ghostly particles that slip through entire planets unimpeded, tell a similar story. Detectors like IceCube, buried deep in Antarctic ice, are primed to catch neutrino showers from extreme cosmic events. Yet scans coinciding with FRB detections reveal no unusual neutrino activity. This is particularly confounding because some FRB models predict neutrino production, especially those involving magnetar flares or collapsing exotic matter. If these processes are happening, they're either not making neutrinos or not making enough to reach us across intergalactic distances. Even electromagnetic counterparts, the X-ray or gamma-ray flashes that should accompany violent astrophysical events, are conspicuously absent for most FRBs. Apart from the lone Milky Way magnetar burst that paired an FRB with X-rays, the vast majority of extragalactic bursts arrive without this high-energy entourage. It's like witnessing a supernova that only emits ultraviolet light, a violation of everything we know about how energy behaves in extreme environments. So where does this leave us? One possibility is that FRB engines are phenomenally efficient, converting nearly all their energy into coherent radio waves with almost no waste heat or collateral emissions. Imagine a cosmic laser so precise it funnels 99.9% of its power into a single wavelength. This would require physics beyond our current understanding of plasma and magnetic fields, perhaps involving quantum effects or exotic states of matter. Alternatively, we might be missing the counterparts because they're arriving in forms we don't recognize. Gravitational wave detectors, for instance, are fine-tuned for specific frequency ranges, the thuds of black hole mergers or the chirps of neutron star collisions. An FRB source vibrating spacetime at higher or lower frequencies could slip through unnoticed. Similarly, neutrinos from FRBs might be too low energy for current detectors, or might be beamed in directions we're not monitoring. The most tantalizing and unsettling scenario is that FRBs are teaching us about entirely new emission mechanisms. Perhaps they're tapping into dark matter interactions or quantum vacuum decays processes that don't produce the usual cosmic fanfare. Or maybe their energy is escaping via dimensions or particles we haven't discovered yet. Every empty search, every silent detector is a quiet revolution, a hint that the universe's playbook is thicker than we imagined, with chapters we've only just begun to skim. As observatories grow more sensitive and coordination between telescopes tightens, the multi-messenger mystery may yet crack open, but for now the silence speaks volumes. FRBs aren't just brilliant flashes in the dark. They're cosmic soloists performing pieces we're only beginning to hear, and the absence of an orchestra might be the most telling clue of all. In the ever-growing catalogue of fast radio bursts, a handful stand out for their eerie resemblance, like cosmic doppelgangers separated by years. Take FRB 150215 and FRB 191108. Detected 4 years apart yet bearing nearly identical dispersion measures, pulse widths and frequency structures. At first glance, they could be twins right down to the subtle drift of their bursts down the radio spectrum. But here's the catch: their arrival directions point to entirely different patches of sky, making it astronomically improbable they share a single origin. This is the FRB twins mystery, and it's forcing scientists to reconsider everything from burst propagation to the fundamental nature of these enigmatic signals. The implications are staggering. If unrelated FRBs can mimic each other so precisely, it suggests universal physics might be sculpting these bursts into predictable forms, like waves crashing onto different shores yet leaving identical patterns in the sand. One theory points to plasma lenses in intergalactic space. Just as a magnifying glass can focus sunlight into similar bright spots, vast clouds of ionized gas might be reshaping disparate FRBs into lookalikes by selectively amplifying certain frequencies and suppressing others. These cosmic lenses could even explain why some bursts appear to originate in voids, their true host galaxies, hidden behind distorting plasma screens that redirect and homogenize their signals. But there's a darker horse in the race. What if the twins are actually the same burst, taking multiple paths through the universe? Einstein's theory of general relativity predicts that massive objects can bend light so severely it follows divergent routes to the same destination, a phenomenon called gravitational lensing. If an FRB's radio waves split around a galaxy cluster or black hole, one path might arrive years later than the other, creating the illusion of two distinct events. The challenge: no known lensing structure along these FRB sightlines is massive enough to produce such a delay, unless, of course, we're missing invisible concentrations of dark matter warping space-time in ways our telescopes can't see. The most tantalizing possibility flips the script entirely. Perhaps FRB twins aren't coincidences or lensing artifacts, but signposts to something far stranger. Some models propose cosmic strings, hypothetical defects in spacetime from the early universe, vibrating at resonant frequencies to produce matched bursts across billions of years. Others suggest quantum tunneling effects in neutron star magnetospheres, where similar magnetic configurations spontaneously generate identical emissions regardless of location. Even the holographic principle gets a nod, with theorists speculating that information encoded on the universe's boundary might project duplicate events into three-dimensional space. Every matched pair forces us to confront the limits of our classification systems. We've long assumed FRBs are like fingerprints, unique signatures of chaotic astrophysical engines. But if nature can stamp out indistinguishable bursts across cosmic distances and epochs, it hints at underlying order we've barely begun to decipher. The twins don't just deepen the mystery, they rewrite the question entirely. Are we seeing individual catastrophes or fragments of a grander pattern, woven into the fabric of reality itself? Deep in the voids between galaxies, hidden from even the most powerful telescopes, lies a ghostly sea of matter that's been missing for decades. Not dark matter, the universe's infamous enigma, but something far more mundane yet just as elusive: ordinary protons and neutrons, the building blocks of stars and planets, mysteriously unaccounted for in our cosmic inventories. This is the missing baryon problem, and fast radio bursts are turning out to be the perfect flashlights to illuminate these shadows. Every FRB's journey through the cosmos leaves a telltale fingerprint: the way its radio waves slow and scatter as they plow through the sparse electrons floating in intergalactic space. That delay, called dispersion, isn't just noise, it's a measuring stick. By calculating how much an FRB's signal stretches during its billion-light-year trek, astronomers can tally up every electron it encountered along the way. And since electrons cling to protons in normal matter like static to a balloon, that count reveals the total baryonic weight of the universe's backroads. The numbers shocked researchers. When you add up all the visible matter, stars, galaxies, glowing gas, it accounts for barely half the baryons predicted to exist based on the universe's early chemistry set by the Big Bang. The rest, until FRBs came along, they'd slipped through every observational net. But now, thanks to bursts like FRB 180924, detected slicing through a galactic filament in 2018, we're getting our first real maps of this hidden infrastructure. Here's where the detective work gets brilliant. Different cosmic environments leave distinct scars on an FRB signal. The diffuse plasma between galaxies stretches the burst gently, like taffy pulled slow. But when the signal grazes a galaxy cluster's superheated halo, the effect is dramatic, a sudden kink in the dispersion measure, betraying the cluster's otherwise invisible bulk. It's cosmic tomography, with FRBs as the X-rays. Already, bursts like FRB 190614 have exposed gargantuan reservoirs of warm, hot intergalactic medium, their baryons too sparse to glow but thick enough to bend radio waves. The real breakthrough came when astronomers cross-referenced FRB data with the universe's large-scale structure. The dispersion measures lined up perfectly with the web-like filaments predicted by simulations, the very threads thought to shuttle baryons between galaxy clusters. Even more astonishing, some bursts' polarization revealed these filaments are magnetized, their fields likely seeded by ancient quasars or galactic winds. But FRBs aren't just confirming theories, they're exposing surprises. Recent studies suggest up to 30% of missing baryons might be hiding in even hotter, more diffuse gas than models anticipated, possibly heated by shocks from long-ago cosmic collisions. Others hint at vast, magnetized bubbles around galaxy clusters, their origins still unknown. With every new burst, we're not just filling gaps in a spreadsheet. We're watching the universe's circulatory system take shape, a web of matter and energy that's been invisible since the dawn of time, and this is just the beginning. Future FRB hunting arrays, like the Square Kilometer Array, promise to detect thousands of bursts annually, each one a probe into the cosmic dark. Imagine mapping every filament, every void, with the precision of a medical scan, not just counting baryons, but tracking how they flow, how they're heated, how they've shaped the universe's growth. FRBs are more than mysteries now. They're the keys to the cosmos's hidden architecture. Scanning the sky for fast radio bursts sometimes feels like mapping a city's lights from space. Vast stretches glitter with activity, while other regions lie stubbornly dark. These are the FRB dead zones, patches of the cosmos where, despite thousands of hours of telescope time and painstaking analysis, not a single burst has appeared. Their absence isn't random. Clustered primarily near the Milky Way's plane and in select extragalactic voids, these silent sectors are cosmic blind spots that might hold as many clues as the bursts themselves. Consider the galactic plane avoidance first. Nearly all FRB detections skew toward high galactic latitudes, directions pointing above or below the thick disk of our own galaxy. At first glance, this seems like an observational quirk. The Milky Way's crowded core swirls with dust, gas, and pulsars that muddy radio signals. But here's the twist: even after accounting for this interference, the avoidance persists. Some dead zones coincide with areas where the interstellar medium is oddly thin, ruling out absorption as the sole culprit. This suggests a deeper link. Perhaps FRB sources themselves steer clear of certain galactic environments, like cosmic creatures preferring specific habitats. Then there's the case of the local hole, a 300 million light-year-wide void where galaxies are sparse and FRBs even sparser. While most bursts trace back to vibrant star-forming galaxies, this underdense region stretching across constellations like Eridanus and Taurus has yielded almost none. One explanation: FRB engines might rely on resources abundant in bustling galactic neighborhoods, young magnetars, dense plasma, or turbulent magnetic fields. The local hole's quiet, aging galaxies, with their dwindling star formation, could simply lack the raw materials needed to power these explosive events. But dead zones aren't just empty negatives, they're boundaries that define where FRBs can exist. Take the Fanelli Gap, a wedge of sky where the CHIME telescope, despite scanning daily, has detected zero bursts. Intriguingly, this region aligns with the ecliptic plane, Earth's orbital path around the Sun. Could something in our solar system be casting a shadow? Dust in the Kuiper belt or resonant interference from the solar wind might subtly dampen certain frequencies, creating artificial dead zones. If true, it would mean some silences aren't cosmic at all, they're illusions born of our own backyard. The most tantalizing voids, though, are the theoretical ones. Quantum cosmology models suggest space-time might foam at ultramicroscopic scales, creating domains where certain radio wavelengths scatter unpredictably. If FRB signals pass through these hypothetical bubbles, they could vanish entirely before reaching Earth, making dead zones not just absences, but windows into the fabric of reality itself. It's a radical idea, but one that underscores a profound truth. In the hunt for fast radio bursts, silence speaks as loudly as any signal. So the next time you see a map of FRB detections, don't just focus on the bright dots. The empty spaces between them are mysteries, two cosmic deserts where the rules might be written differently. And as telescopes grow more sensitive, these quiet patches may yet reveal their secrets, whispering the limits of where and how the universe chooses to scream. In the radio spectrum where fast radio bursts dominate, there's an invisible wall at 8 GHz of frequency ceiling beyond which no FRB has ever been detected. This cutoff persists despite decades of searching with instruments capable of detecting signals 10 times higher, leaving astronomers puzzled. Why would cosmic phenomena capable of generating such extraordinary energy suddenly go silent at frequencies commonly used by earthly satellite communications? The mystery begins with the telescopes themselves. Higher frequency radio waves, those above 8 GHz, behave differently than their lower frequency counterparts. They're more easily absorbed by water vapor in Earth's atmosphere and interstellar dust, creating natural observational hurdles. Yet this alone can't explain the complete absence of detections, since radio observatories like ALMA and the VLA routinely study objects emitting at hundreds of gigahertz. The silence suggests something fundamental about FRB emission physics, not just observational limitations. Diving into potential explanations, one compelling theory points to the emission mechanism itself. Most FRB models involve coherent radiation, think laser-like precision rather than a light bulb's scattered glow. At lower frequencies, this coherence can be maintained as electrons spiral along magnetic field lines or as plasma instabilities amplify signals. But above a critical threshold, these processes may become dephased, their orderly radiation dissolving into incoherent noise. Picture an orchestra playing in perfect harmony until, at a certain pitch, the instruments can no longer synchronize, the music collapses into chaos. Another angle involves the environment surrounding FRB sources. Many bursts likely originate in magnetars enveloped by dense plasma, a soup of charged particles that acts like a frequency-dependent filter. Higher frequency radio waves interact more strongly with this plasma, potentially being absorbed or scattered before escaping. It's akin to how sunlight gets redder at sunset as blue light scatters away, only here, the sunset happens across the electromagnetic spectrum, leaving only the cosmic equivalent of reds and oranges, the sub-8 GHz signals we detect. Yet the plot thickens when considering the few high-frequency searches that have been conducted. Some targeted repeating FRBs during active phases, expecting harmonics or overtones that never materialized. Others scanned galaxies hosting known FRBs at millimeter wavelengths, coming up empty. This uniformity hints that the cutoff isn't just statistical, it's intrinsic, woven into the fabric of how these bursts are born. The most tantalizing possibility, we might be witnessing the limits of known physics. Certain exotic models like quantum vacuum breakdown or action-mediated emission predict natural frequency ceilings based on the energy scales of hypothetical particles or spacetime effects. While speculative, these ideas underscore a humbling truth. FRBs aren't just mysterious because they're distant. They're challenging the very frameworks we use to understand radiation itself. As telescopes push into ever higher frequencies with greater sensitivity, the 8 GHz wall stands as both obstacle and invitation, a boundary saying, look deeper. Whether it's the final note in a cosmic symphony or the static before a revelation remains to be seen. But one thing's certain, in the hunt for FRBs, the frequencies we don't hear may be just as important as the ones we do. Imagine a bell tolling inside a cavern, each reverberation blending with the last until the echoes become indistinguishable from the original clang. Now replace the bell with a magnetar and the cavern with a superheated plasma fog stretching light years across. This is the essence of the FRB echo chamber theory, a radical proposal that some repeating bursts might not be direct signals at all, but cosmic mirages, their intricate patterns sculpted by radio waves ricocheting through turbulent stellar nurseries or the remnants of exploded stars. At the heart of this idea lies a simple but profound shift in perspective. Instead of originating from a single, pulsing object, certain FRBs, especially those with intricate sub-bursts or frequency drifts, could be the product of a signal bouncing wildly within a dense, magnetized environment near its source. Picture a flashlight beam bouncing between mirrors in a hall of mirrors, each reflection subtly altered by the surface it strikes. In this cosmic analogy, the mirrors are plasma clouds swirling pockets of ionized gas left behind by supernova or violent stellar winds, and the flashlight is the original burst, perhaps a simpler emission from a magnetar or collapsing star. The theory gained traction when astronomers noticed something peculiar about FRB 180301's polarization. Its radio waves arrived twisted in a way that suggested passage through an extreme magnetic field, but the twist was too severe to have accumulated during the burst's intergalactic journey. The only plausible explanation, the signal had encountered a localized maelstrom of plasma near its birth, possibly a hypermagnetic nebula or the debris field of a recent stellar collision. Later studies of other repeating bursts revealed similar fingerprints, signals that seemed to remember their turbulent origins long after escaping their host galaxies. Critics argue that echo chambers shouldn't produce such coherent patterns. Scattering in dense plasma typically smears radio waves beyond recognition, like a shout echoing through a storm. Yet some FRBs maintain startling clarity despite their complex structures. Proponents counter that certain plasma configurations like ordered magnetic filaments or shock fronts could act as waveguides channeling reflections with minimal distortion. It's the difference between echoes in a cluttered attic and a cathedral. One scatters sound chaotically while the other preserves its musicality, the most tantalizing implication. If echoes are masquerading as original bursts, we might be dramatically overestimating FRB energies. A single, parent burst, reflected and amplified by surrounding plasma, could spawn multiple apparent detections, each a fraction of the true source's power. This would resolve the puzzle of how some repeating FRBs sustain such extravagant outputs over centuries without exhausting their engines. Yet the theory opens its own can of worms. Why do only some FRBs show echo-like features? Could certain galactic environments like young star clusters with abundant plasma be predisposed to creating these cosmic reverberations? And if echoes are so convincing, how many one-off bursts might actually be reflections of older, unseen events? The echo chamber hypothesis doesn't just challenge how we model FRBs, it forces us to reconsider what counts as a signal in the first place. Are we listening to the universe's scream or the walls it echoes off? The answer might rewrite not just the story of FRBs, but our understanding of how radiation navigates the cosmos's hidden labyrinths. Binary star systems should be prime real estate for fast radio bursts, cosmic duos where one star's death leaves behind a magnetar or neutron star locked in a gravitational dance with its surviving companion. Theory predicts these setups could generate perfect conditions for FRBs. Tidal forces stripping material from the living star, feeding violent outbursts from its collapsed partner, and orbital mechanics creating predictable bursts every time the pair swings close. Yet despite scanning thousands of binary systems across multiple galaxies, astronomers keep coming up empty. This absence isn't just puzzling, it's forcing a wholesale re-examination of how FRBs are born. The first red flag emerged when researchers cross-referenced FRB host galaxies with catalogs of known binary systems. Take the Small Magellanic Cloud, a satellite galaxy brimming with X-ray binaries, pairs where a neutron star siphons gas from a stellar companion. These systems produce regular flares across the electromagnetic spectrum, but not a single confirmed FRB. Even more confounding are the so-called spider systems, where a pulsar orbits so close to its partner that its radiation is slowly evaporating the other star. These extreme binaries should be FRB factories, their turbulent interactions launching plasma shocks ripe for radio bursts, yet the silence persists. One possible explanation cuts to the heart of FRB theory itself. Maybe magnetars, the leading candidates for burst production, rarely form in binaries. When massive stars explode as supernova, the resulting kick can send newborn neutron stars careening through space at hundreds of kilometers per second, severing gravitational bonds with any companions. Only in exceptionally gentle explosions or with unusually massive partners would a magnetar remain bound. Supporting this, population studies suggest less than 10% of known magnetars reside in binaries, a scarcity that could explain the FRB drought. But the plot thickens when considering beaming effects. FRB emission is thought to be highly directional, like a lighthouse beam sweeping the cosmos. In a binary system, that beam might only align with Earth during brief orbital phases, making detection statistically unlikely. Compounding the issue, plasma spewed from the companion star could distort or absorb radio waves, effectively cloaking the bursts from our view. It's like trying to spot a blinking buoy through fog. The signal might be there, but the conditions conspire to hide it, the most tantalizing possibility. We might have already detected binary FRBs without realizing it, some repeating bursts with periodic activity like FRB 180916's 16-day cycle fit neatly with theoretical binary orbital periods. Without visible counterparts, though, these remain circumstantial matches. Future instruments monitoring both radio and X-ray signatures could break the deadlock, catching the telltale flicker of a companion star's heated surface or the X-ray glow of accreted material. Until then, the missing binaries stand as both challenge and invitation, proof that the universe still guards its most explosive partnerships with fierce secrecy. And every empty search reminds us, sometimes what we don't find teaches us more than what we do. Neutron stars aren't the predictable timekeepers they appear to be. Every so often, without warning, one will suddenly spin faster, a bizarre hiccup in its rotation called a glitch. These cosmic stumbles have baffled astronomers for decades. But what if these seemingly random speed jumps aren't just isolated quirks? What if they're the hidden triggers behind some of the universe's most mysterious signals, fast radio bursts? The connection starts with magnetars, those ultramagnetic neutron stars already suspected of powering FRBs. These stellar corpses are notorious for their volatility, their crusts under such immense strain that they occasionally crack like porcelain under pressure. When that happens, two things occur almost simultaneously. The star's rigid outer layer fractures, releasing pent-up energy, and its superfluid interior, normally frictionless, couples abruptly to the crust. The result, a glitch. The star's rotation lurches forward, speeding up by a fraction of a second. And crucially, this sudden shift could violently jerk the magnetar's already twisted magnetic field lines, snapping them like overstretched rubber bands. That snap is where the magic happens. According to simulations, a magnetic reconnection event following a glitch could channel the energy of 1,000 suns into a tightly focused radio beam, essentially an FRB. The timing fits too. Glitches in known magnetars often precede X-ray or gamma-ray flares by milliseconds to minutes, a sequence eerily similar to the paired emissions seen in the Milky Way's homegrown FRB from SGR 1935 plus 2154. Even the energy budgets align. A typical magnetar glitch releases enough rotational energy to power an FRB several times over, but not all glitches are created equal. Some neutron stars exhibit anti-glitches, where they inexplicably slow down instead of speeding up. Intriguingly, a handful of repeating FRBs show similar behavior. Their bursts sometimes arrive with slightly longer intervals, as if their internal clocks have hit a speed bump. Could these be the radio echoes of an anti-glitch event, the magnetar's rotation briefly dragging against some unseen cosmic break? The plot thickens when you consider the aftereffects. Post-glitch, many neutron stars experience months-long recovery periods where their spin rates gradually relax back to baseline. This mirrors the cyclical dormancy of repeaters like FRB 121102, which goes silent for months between outbursts. The parallel is hard to ignore. Perhaps FRB active magnetars are simply those caught in a relentless loop of glitch and recovery. Their bursts the cosmic equivalent of a stress fracture screaming under pressure. Yet skeptics point out glaring gaps. Only a fraction of observed glitches in known magnetars coincide with detectable radio emission. Even the most active glitches, like the Crab pulsar, have never been caught producing anything resembling an FRB. This suggests that if glitches are involved, they're not the whole story, perhaps requiring some additional ingredient, like a surrounding plasma nebula or a companion star's wind, to catalyze the radio burst. The most tantalizing clue might come from the glitches themselves. Some exhibit slow-rise behavior, where the star's speed change isn't instantaneous but unfolds over days or weeks. If FRBs are linked to these events, it could explain why certain repeaters show clustered bursts not as separate explosions, but as a single, drawn-out reconnection process glimpsed in stages. It's a theory that turns the traditional view of FRBs on its head, not as isolated sparks, but as brushfires spreading across a magnetar's tortured magnetic field. Whether glitches are the smoking gun or just one piece of the puzzle, their study offers something invaluable, a controlled experiment. Unlike cosmological FRBs, we can monitor galactic magnetars continuously, watching for the telltale spin shifts that might presage a burst. Every glitch is a chance to test the connection, to catch the universe in the act. And if the pattern holds, we might finally have a working model for how these enigmatic signals are born, not in chaos, but in the precise, if violent, mechanics of a spinning star's breaking point. Imagine trying to measure the height of a mountain through a haze of shifting fog. Only the fog isn't just obscuring your view, it's actively bending and warping the mountain's silhouette. That's the essence of the FRB foreground problem. When these cosmic bursts race toward Earth, they don't travel through empty space. Their signals slice through galaxies, gas clouds, and turbulent plasma strewn across billions of light years. Each encounter leaves its mark, subtly distorting the burst's properties in ways that can turn straightforward distance measurements into a cosmic hall of mirrors. Take dispersion measures, the gold standard for estimating an FRB's distance. By calculating how much a burst's lower frequencies lag behind its higher ones, astronomers can tally the electrons it encountered en route. But this assumes all that dispersion happens uniformly in the vast intergalactic medium. In reality, if the signal passes through a foreground galaxy or cluster, its electrons add an unaccounted-for delay, like a hidden toll booth on a highway. The result, a burst that appears farther away than it truly is, its distance overestimated by millions of light years. The reverse can happen too. Some models suggest dense plasma screens might compress dispersion, fooling telescopes into thinking a burst is closer than reality. The distortions don't stop there. Foreground galaxies can act as cosmic prisms, their gravity bending FRB signals via gravitational lensing. This splits the burst into multiple images arriving at slightly different times, a phenomenon already seen in quasars, but far trickier to detect with FRB's fleeting nature. Even more insidious is Faraday rotation, where a foreground galaxy's magnetic field twists the polarization of passing radio waves. Astronomers have caught this in action with FRB 190614, whose signals showed extreme polarization changes likely caused by a galactic halo it pierced through. These twists aren't just noise, they're clues revealing hidden magnetic fields in galaxies too distant to study otherwise. Yet the biggest headache comes from dark galaxies, invisible dwarfs made mostly of gas with too few stars to spot optically. These stealthy structures, predicted by simulations but notoriously hard to detect, could be littering the cosmic highways FRBs travel. When a burst dispersion measure spikes unexpectedly, it might signal passage through one of these phantom galaxies, their presence etched only in the radio waves they subtly alter. The kicker, we may already have a catalogue of such encounters. FRB 150615 signals showed bizarre, uneven scattering that defied intergalactic medium models, a possible fingerprint of a dark galaxy's turbulent plasma. The solution isn't just better telescopes, it's cosmic triangulation. By cross-referencing FRB distortions with deep optical and infrared surveys, astronomers are building 3D maps of the universe's matter distribution, pinpointing where foreground galaxies likely lurk. The CHIME telescope's recent discovery of an FRB behind the Coma cluster demonstrated the power of this approach. The cluster's immense gravity magnified the burst while its plasma left a detectable imprint, allowing researchers to peel away the foreground effects like layers of an onion. What makes these interventions so fascinating isn't just the challenges they pose, it's the opportunities. Every distorted FRB is a free probe, its twists and delays mapping the invisible architecture of cosmic structures we'd never see otherwise. The foreground problem forces us to confront an essential truth. In astronomy, there's no such thing as empty space. Every signal is a messenger, carrying tales not just of its origin, but of every hand that shaped its journey. After decades of hunting, we've reached the grand finale of the fast radio burst mystery, the ultimate question. What cosmic engine could possibly unleash such staggering energy, and do it with the precision of a Swiss watch and the randomness of a lightning storm? The answer isn't just hidden in one theory, it's scattered across the extremes of astrophysics, waiting to be pieced together. Let's start with the reigning champion, magnetars. These ultramagnetic neutron stars pack the mass of a sun into a city-sized sphere, spinning faster than a jet turbine and wrapped in magnetic fields so intense they could rip atoms apart from 1,000 miles away. When their crusts fracture under magnetic strain, the resulting starquakes unleash energy equivalent to a solar flare compressed into milliseconds, a plausible recipe for FRBs. Yet even these cosmic powerhouses struggle to explain the most energetic bursts. To match the luminosity of FRBs from the early universe, a magnetar would need to operate at energy levels bordering on the impossible, converting nearly all its magnetic fury into radio waves with near-perfect efficiency. It's like demanding a nuclear reactor produce a lightning bolt without any heat or noise. Then there's the wild card, collapsing black holes. Picture a supermassive neutron star, a blitzar, teetering on the edge of becoming a black hole. Held up by centrifugal force, it spins frantically until friction slows it just enough. In its final milliseconds, as the star's core succumbs to gravity, the collapsing magnetic fields could launch one last catastrophic radio scream, a burst so bright it outshines galaxies. This model neatly explains one-off FRBs but falters when confronted with repeaters, unless, of course, black holes can somehow stutter in their formation, a notion that stretches current physics to the breaking point. For those who prefer their cosmic engines stranger still, superconducting cosmic strings offer a tantalizing alternative. These hypothetical relics from the Big Bang, infinitely thin, vibrating filaments of spacetime itself, could snap under tension, releasing energy in focused radio beams. The math is elegant. A string just one atom thick, vibrating at near light speed, could power an FRB with energy to spare. But here's the catch: no one's ever detected a cosmic string. They exist purely in theory, a ghostly solution searching for proof. And then there's the dark horse, action stars. These hypothetical clumps of dark matter particles could decay in violent bursts, their energy converting to radio waves as they interact with galactic magnetic fields. It's a fringe idea, but one that could explain FRBs appearing in seemingly empty voids, places where conventional stellar engines shouldn't exist. The truth might lie in a cosmic cocktail, multiple mechanisms operating across the universe. Magnetars could dominate in young, star-forming galaxies, their bursts amplified by surrounding plasma. In the voids, perhaps quantum vacuum breakdowns or collapsing dark matter structures take over. And for the strangest repeaters, maybe we're seeing something entirely new, a cosmic pendulum swinging between dimensions, or a black hole's ergosphere ringing like a bell. What makes FRBs so exhilarating isn't just the mystery, it's the scale of possibility. Every detected burst forces us to ask, are we seeing the universe's known limits or the first hints of physics beyond them? The answer won't just solve a puzzle, it could redefine how energy itself operates in the cosmos. And until then, the universe keeps sending these cryptic signals not just as questions, but as invitations to dream bigger. Fast radio bursts have taken us on a journey through 30 of the cosmos' most electrifying puzzles. From their mind-bending energy outputs and eerie repetitions to their ghostly origins in the voids between galaxies. Each time we think we've grasped a piece of the puzzle, the universe tosses another curveball. Solve one mystery, like linking an FRB to a Milky Way magnetar, and suddenly two more appear. Why don't all magnetars produce bursts? Why do some FRBs seem to emerge from nothingness? It's as if the cosmos is playing a game of cosmic whack-a-mole, where every answer sprouts new questions faster than we can swing. Consider how far we've come. What started as a single anomalous blip in Parkes telescope data has exploded into a field of study revealing the universe's hidden architecture. FRBs have exposed missing baryons in cosmic filaments, mapped the magnetic ghosts of ancient galaxies, and even hinted at physics beyond Einstein. Yet the deeper we dig, the stranger it gets. Why do some bursts arrive with the precision of a metronome while others scatter like shrapnel? How can a signal traverse billions of light years only to vanish without an afterglow? The more data we collect, the clearer it becomes. These aren't just cosmic oddities. They're signposts pointing toward gaps in our understanding of matter, energy, and space-time itself. The future of FRB science is a frontier wide open. Next-generation telescopes like the Square Kilometre Array will catch thousands more bursts, each a forensic snapshot of the universe's invisible scaffolding. Gravitational wave detectors might finally spot the ripples that should accompany these energetic events, or their continued silence could force us to rewrite the rules. And who knows, the key might come from an unexpected corner, a lab on Earth recreating magnetar-like magnetic fields, or a breakthrough in quantum gravity that explains why some bursts seem to defy dispersion altogether. But here's the most thrilling part. You don't need a radio dish to join the hunt. The mystery of FRBs belongs to everyone. Maybe your favorite theory, alien megastructures, vibrating cosmic strings, or something no scientist has dreamed up yet, will spark the next big discovery. So tell us in the comments, which of these 30 mysteries fascinates you most? Is it the eerie 16-day cycle of FRB 180916? The way bursts from voids mock our models of cosmic structure, or the tantalizing possibility that we're glimpsing an entirely new class of physics? One thing's certain, the universe isn't done surprising us. Every flicker of radio static carries the potential to rewrite textbooks, to reveal hidden dimensions of reality, or to remind us in a cosmos brimming with wonders how much we have yet to learn. The story of fast radio bursts isn't just about the signals, it's about the boundless curiosity that keeps us listening.